So I will tell you something about strongly lensed supernovae and what we can do for cosmology. Some of the things we have done in the past and what we can expect in the future. Um, so before I tell you about all this, I just wanted to advertise the. Can we take away this?
Oh yes,
Yeah,
sorry.
the things.
The bar.
Yes. Before I tell you about this, I just wanted to advertise these postdoc fellowships that we have in our institute, which are related to astrophysics and cosmology in with the Vera Rubin Observatory. So I'm guessing there are some people here that could be interested, or you know people that are interested. Yeah, the salary is very good, and the application is something similar to Marie Curie. So if you have, you can take a look at the website here. And yeah, if you want to know anything more, just please talk to me. And you might ask, so where is the Center of Astrophysics and Cosmology? Well, it's in the University of Nova Gorica, but it's actually just across the border in the Vipava Valley, only 45 minutes from here. So to give you an idea about our institute. So back to what I was going to tell you. So before I can tell you more about strongly lensed supernovae, I have to just mention just briefly about strong lensing as a tool to study the high redshift universe. So basically, every time we have some massive object, which can be a galaxy or a galaxy cluster, in our line of sight, it can happen that the light that travels from the background object in the vicinity of this lens, it can be deflected. And light is not only deflected, but it can happen so that we have, due to strong lensing, we can have multiple images of the same object. And given that these images will travel to us in different paths, and this, how the light will travel under these different paths depends on how the universe is expanding. It turns out that these time delays are also sensitive to the Hubble constant. And this method was actually proposed back in 1964 by Revstal. And so far, the state of the art has been to use time delays for cosmology by using quasars. And this is the result from the Holy Cow collaboration, which has used 6 quasars, time delays from 6 quasars in order to infer the Hubble constant with a few percent precision. And you know well that we have this so-called Hubble tension, where the Hubble constant differs whether you are measuring with early or with late time probes. But the original idea of Revstal was to use supernovae for time delay cosmography. But the problem is that supernovae are rare, and we cannot really predict when they can happen, really. And in fact, it was after 50 years after this Revstal method was proposed that the first supernova with multiple images was found in the Hubble Space Telescope data, and that was a core collapse type of explosion. Nevertheless, the lensing models were able to predict that a fifth image will reappear after a year. Also, and this was a great way to test all the different lensing models. And given that, even though it was a core collapse type of explosion, the fact that the model of the cluster was quite well pinpointed due to the all the observational constraints, such as the spectroscopic redshifts of the multiple image galaxies, and the time delays were quite well measured, then it was possible to infer the Hubble constant, of course, not with a competitive precision such as the Schurz collaboration or the CMB, but still it's a way forward. So I told you that strong lensing is great if you want to get multiple images of the same object, but it also provides magnification of the background object. So it allows us to observe objects that otherwise would be unobservable with our current telescope. And how can we use this property of nature that is there for free? So one example is if we take a look at the Hubble diagram today, we will see that at high redshift, which means like, let's say above a redshift 1, type 1a supernovae that we have on the Hubble diagram. There are only a few of them. And if we take a look at their spectra, we will see that they are quite noisy and they're not really, we cannot really do any detailed analysis of this spectrum. And you can ask, so why do you want to do any detailed analysis of high redshift type 1As? Well, basically, given that now that we have the Raman Space Telescope coming, and we will use it to make more, to estimate other also cosmological parameters, such as the parameter like dark energy and so on. Then when we're doing this, we're making the assumption that high redshift supernovae are the same as those at low redshift. But it could be that there is some kind of evolution in the intrinsic properties of supernovae that we're not out counting yet when we're making cosmology. So one way to test this is to compare the spectra of high redshift with the low redshift supernova and see if there are any signs of worry. And this possibility arose when we had this strongly lensed supernova PS110FX, which probably had multiple images, but still they were not able to resolve because there was a ground-based survey that found this. And this supernova was magnified 30 times. So type 1a that was magnified 30 times by foreground galaxies. So then what we did is to compare this spectrum of the supernova with low redshift and a medium redshift sample of supernovae that we think are more or less vanilla. And we didn't find anything to worry at the moment. Going forward in 2016 with the IPTF, which is the Intermediate Palomar Transient Factory, which was scanning the sky and looking for new transients, and was really good at finding nearby, which I mean less than 0.1 redshift supernovae. So then when a supernova arose in the data that was at redshift 0.4, it was already a flag that there's something weird going on. And then in the same location, there was a elliptical galaxy at redshift 0.2. So then the idea was that this elliptical galaxy was the lens, and the supernova was at in the background at redshift 0.4. But given that it's a ground-based survey with a low resolution, you need to get high resolution imaging, such as Hubble Space Telescope or adaptive optics, to see this. And in fact, the images show that there are 4 images of the same supernova multiply image, and then there's the lensing galaxy in the middle. And just by comparing the observed with the expected light curves of supernova at redshift 0.4, we can immediately see that there's magnification of at least 50 times was required to explain the brightness of this event. And then you can see that there are different brightnesses of the images. So there's a bit more complicated than this story. So there's some micro lensing and also dust extinction in the line of sight that has to be taken into account. And then in 2022, there was this another supernova, so-called supernova Zwicky, found with the Zwicky Transient Facility, which is the follow-up, the successor of IPTF that I mentioned before, with just larger camera. So it was a very similar event to what I explained before, and also the images could be resolved only with space. So this is the Hubble Space Telescope data, and unfortunately, the time delays were very short, so it was not possible to use it to do any estimates of the Hubble constant. And then going forward to this year, so 2023, we have the supernova Hope, which was found in James Webb data in the PEARLS program. And this one is a supernova lensed by a galaxy cluster. And here we can see the three different images. And at the moment, the time delays are being measured, and the papers are coming soon. So actually, in few years, we have gone from 0 to several events, and I don't even have time to go through all of them. But my point here that I want to make is that we are seeing more and more of these events, and somehow it seems like galaxy clusters are even more suitable for measuring the Hubble constant, given that the time delays are longer, while those that we have seen so far, with the examples that I mentioned, seem they are quite short and not really probable. We cannot probe them for measuring the Hubble constant simply because they are less than 24 hours. Talking about strongly lensed supernovae, I have to mention the so-called lens-watt collaboration, which is just a bunch of people that are interested in studying lens supernovae. And for this purpose, we have HST time to follow up lens supernovae, and so far I've shown you some data that from Supernova Wiki that we have published so far, and the future will be that there is a accepted proposal for a joint HST and James Webb that will follow up imaging and spectroscopy for up to 3 supernovae, lens supernovae, which hopefully they will give us a competitive estimate of the Hubble constant. Just to summarize here, I hope I told you that it's very interesting to use galaxy cluster to look for lens supernovae. Well, of course, because of measuring their time delays and to measure the Hubble constant, which is now being debated. But also, one is if we can say that their magnification can be estimated directly because they are standardizable candles. Then we can even use them to test the lensing models, which we know that they suffer from several degeneracies. But then for core collapse supernovae, we still have a lot of things that we can do with lensed core collapse supernovae. I mean, just to use the fact that these are magnified, so we can probe them up to high redshifts where we don't have that really many supernovae of this core collapse type, and perhaps even find the first population 3 supernovae, which are still haven't been seen yet. So in the past, what we have done is to run a ground-based survey at the VLT with the Hawkeye instrument in the near infrared, where we expect that the light from distant supernovae is shifted. So basically, getting data each month of several galaxy clusters, and then try to find lens supernovae. And I go here to the results. Basically, what we found was 5 high redshift supernovae, all of them core collapse, but they all had a significant magnification. And the highest redshift one is at 1.7, which I guess for those that are working with core collapse supernovae is very high redshift supernova. And then what can we do with these discoveries? Even though, given that we were looking through the magnified view of the galaxy cluster, So this gave us a lot of sensitivity even to high redshift, and we can use the survey to say something about the high redshift supernova core collapse rates, and then even compare it to the star formation history, which is interesting because then we know that the supernova rate, the core collapse rate, scales with the star formation history, and thank you. And what else we can do? Staring at galaxy cluster, we also found type 1a supernovae that were inside the cluster, and this is interesting in itself because cluster supernova rates type 1a are thought to be, let's say, more simple. So let's say we can even say something about the delay time distribution, which we heard today during the morning talk. What about the future? I mentioned here 2 surveys that are coming very soon, and this is the Vera Rubin Observatory and the Roman Space Telescope. And so the Rubin Observatory being a ground survey, it has this set of filters, and Roman, of course, being space-based survey, it extends, it can go all the way to the infrared. And there are several works that have tried to put some forecasts for how many galaxy lengths the supernova we can expect. And then even that we probably will need something like 20 lengths supernovae, but we will still need a very good spectroscopic follow-up in order to get the pinpoint the time delays if we want to get the Hubble constant with 1% precision. Of course, with the LSST, with the Vera Rubin Observatory, with the Roman Space Telescope, we will not get that many, but these will be at much higher redshift because of simply because how the filters are. So simply because supernovae, let's say type 1a, from the ground are not really observable simply because their light, which peaks in the optical, is shifted to longer wavelengths. So we need to go to the infrared. But then we can also look for supernovae which are in the multiply imaged galaxies that we see in clusters. So here is an example of a galaxy cluster, and let's say this is a galaxy that we see in multiple images. So if a supernova explodes in the first image, then from the lensing model, I can even predict that another image will appear in, let's say here, the example of 60 days or so. So then I can know when to trigger follow-up observations. And so at the moment, there is an effort from our group and the Space Telescope Institute in the US, which we are trying to develop all the infrastructure that is needed in order to use galaxy cluster for this purpose. And we are working on what kind of numbers of supernovae we can expect in the cluster fields. And this is some details if you're interested in what are the plans of using lens supernovae and the Roman Space Telescope. So with this, I would like to summarize, and I hope I told you some interesting things that we can do with galaxy clusters as gravitational telescope, and some of the things in the past, what we can use in order to say something about the spectroscopic properties of type 1As as standard candles, and searching for supernovae in order to say something about their rates at higher redshift. And you can see that in since 2014 until we have gone from 0 to more than 6 events, and all of them have given us some very nice insights about astrophysics and cosmology. And the future, of course, as all the talks we heard these days, is bright, and we can expect a lot of more coming for this topic. So thank you.